Okay, good morning everyone. I hope you can all hear me well. If you can hear me, can you just confirm? Okay, great. Thank you so much. So let me quickly revise what we did yesterday. So in the last class, we looked at the naive Bayes classifier, and we went to a rather detailed discussion on what naive Bayes is, how it works, what is the math behind it. And if I have to quickly verify or confirm or summarize, I can say that the naive Bayes classifier works on the Bayes theorem. Bayes theorem helps us to evaluate something called as conditional probability. We use conditional probability in the sense of our data to say that we need to find out the probability of a particular class given a certain data. Okay. Now, to evaluate the probability of data given a class, we use a naive assumption that the features are mutually exclusive. And if we make that assumption that the features are mutually exclusive, then we can evaluate something like this. Okay, we can evaluate the probability of a class, a probability of data given a class by the product of the individual features given the class. Okay, and we saw that this only works out if the features are mutually exclusive, that is not correlated. Okay. Nonetheless, we went ahead and we evaluated different terms of probabilities, okay, depending upon what the data is. We saw that this is fairly simple to do. It is not as complex. We can, of course, we can use methods from scikit-learn that will a package like scikit-learn that has implemented all these algorithms, and we simply can use it. That is one way. But even if we have to code it, this is not very complex. It can actually be coded. We saw how we can use these individual probabilities. So for our case of this artificial medical data, that it takes roughly around 20 parameters to evaluate the features. We saw some advantages and disadvantages of naive Bayes in terms of what will happen if there is a large number of data, what will happen if, or how long will it take, how many parameters will it take, and so on. So few advantages of naive Bayes: it is simple to implement, it works very well on large data sets, and and disadvantage of naive Bayes is if the features are correlated, then we may have a trouble. Okay. So let us move then ahead to our next classifier, or next very commonly used classifier. It's called decision tree, and I hope some of you may have heard this already, but we'll go today a bit deep to understand how the decision tree works. What is the core concept? What is the math behind it? Okay. Let me also remind you that when we are defining these algorithms, or when we are exploring these algorithms, what we are trying to do is we are trying to understand what is there inside this box. Okay. Or we are trying to estimate what comes inside this box. So if I give inputs like this to my model and I expect an output like this, we're trying to understand what is the underlying target system. And we use different models to explain what is happening inside. So KNN has its theory. It explains that, okay, something, KNN says maybe inside is working like this. Naive Bayes says that, oh no, I think it is working based on Bayes theorem. Decision trees will say, no, I think it is working on decision trees. So different algorithms are making different estimates as to what they understand is happening inside. Okay, and we as data scientists, we are exploring which algorithm fits the data best. Okay, and whatever fits the data best, that is our choice of algorithm. Okay, of course we have other considerations also, but primarily the algorithm that fits the data best is our choice. Now, when we look at decision trees, a few things as an introduction. When we look, decision trees, it builds models in the form of a tree structure. Okay, So in the next slide, I'll show you what a tree structure is and what do I mean by tree structure. But decision tree, it makes a model in that form. Okay, it makes it in the form of a tree. What it does is it breaks down a data set into smaller and smaller pure subsets. Okay, while tree is incrementally developed. Okay, so I look at my data, and my data has multiple points. What we are trying to do is we are trying to break down smaller and smaller and smaller concepts, smaller buckets, and each bucket we are hoping that we have something called a pure subset. Okay, while when we have a pure subset, we know that okay, I don't need to divide it further. I can stop at that point. Okay, so of course it may be a bit confusing at this point. Just wait for one more slide. In the next slide, things will become clearer. Okay. So we are trying to make smaller and smaller pure subsets. Okay, while we are doing this, we are incrementally developing the tree. Okay, now there are two kinds of nodes on a tree. We have decision nodes and we have leaf nodes. A decision node is somewhere from which we'll take a decision and divide it into multiple parts. A leaf node is somewhere we'll end the tree. The tree will not continue further at that point. Okay, so we have decision nodes and we've got end nodes. And decision tree can handle both. It can handle both categorical and numerical features. So in today's discussion, we will keep our discussion limited to categorical because it will help us understand what is happening. But decision trees can handle both numerical and categorical features. Okay. That's a small introduction. Let us now get inside to decision tree. So here we look at this data. Okay, we look at our data, which is again, this is again artificial data that we have created just to explain a point. We have 14 rows, of which one row is hidden behind this text, but that's fine. That should not affect us. And we have four features: outlook, temperature, humidity, windy, and we have one target variable, play golf. Okay. Outlook can take multiple values. The outlook is a categorical feature which says it can take rainy, overcast, or sunny. Temperature can take three values: hot, mild, or cool. Humidity can take two values: high or normal. Windy can take two values: true or false. And play golf can be either yes or no. Okay. The data is simple. The data says that depending upon these environmental conditions, we will decide if it is a good day to play golf or it is not a good day to play golf. Okay. As I said, this is artificial data, not important. Nonetheless, we are looking at to understand some concept. Okay. So let's look at an example. If the outlook is rainy, temperature is hot, humidity is high, and windy, it is not windy, then we will say that we are not going to play golf. Okay. If the outlook is overcast, humidity is hot, temperature is hot, humidity is high, and windy is false, then we will say we'll go and play golf. Okay. So some simple data. Now, what decision tree does, it says that if I get a data like this, I'll try to create a decision tree, okay, a tree structure like this. In this tree structure, we can see that there are decision nodes. So this is a decision node outlook. Why? Because once we choose outlook, we go to three different options of sunny, overcast, and rainy. We can see that this is a leaf node because at this point, the node ends at yes. There are no more continuations. So we example of decision node, example of leaf node. So at the end here, 1, 2, 3, 4, 5, we have 5 leaf nodes and we've got decision nodes in between. Okay. How to read this graph? This graph says, first, at the beginning, we will look at the feature called as outlook. Okay. Outlook feature, as we see from our data, has three possible options: sunny, overcast, and rainy. If the outlook is overcast, we will not see anything else. We will simply say, yes, play golf. Okay. If the outlook is sunny, we will see the next feature called as windy. Okay. And we'll see windy has again two options, false or true. If windy is false, we say, okay, we have our answer, we will play golf. If windy is true, we'll say we will not play golf. Rather, if the outlook is rainy, we'll say, let us check humidity. If humidity is high, we will say, no, do not play golf. If the humidity is normal, we say, okay, play golf. Okay, so I have a question. How can we choose root node as outlook? Excellent question, actually. In fact, that is the normal question that someone should have after looking at this graph. Just give me a moment. In the next slide, I will start explaining why outlook and other things. But at this point, we are just trying to understand, once we have a tree structure, which decision tree algorithm will help us to create. Once we have the tree structure, how do we use the tree structure? Okay. So in this case, we have seen, let us look at some examples of our data and let us see if this tree structure represents this example or not. Okay. Maybe if we pick up example 6, we will see first the outlook is sunny. So we'll go, okay, outlook sunny, we are in this point. Then look at windy. So for outlook sunny, windy is true. So okay, windy is true. And we say no, don't play golf. We said no, don't play golf. Excellent. We see that in example 6, the structure works rightly. Okay. Let's take another example, maybe example 12. Example 12 says outlook is overcast. Outlook is overcast. We don't need to see anything else. So I don't need this, I don't need this, I don't need this. I see yes. And we say that, okay, example number 12 holds true as well. Let's look at another example, maybe example 2, outlook rainy, yes. Humidity high, yes. Play golf, no. Play golf, no. Okay, so we see that at least for the 3 examples that we tried, that this decision tree faithfully represents this data. Okay. Now, a few questions, as you rightly said, is why did we start with outlook? Okay. After choosing outlook, when outlook is sunny, why did we take windy? Okay. Why have we not, in this entire tree, we have not used temperature at all? Okay. So these are questions that would automatically come into your mind. And if we were discussing on a call, I would probably have asked you, what do you think and why do you think, what are the reasons? Nonetheless, in chat, it is difficult to do these kinds of discussions. Let me go ahead and start explaining how these things work out. Okay. So before we try to understand how these things work out, we need to know a little bit of math, which is relevant to our algorithm. Okay. And a few concepts that we need to know. One of those concepts is called as entropy. I hope some of you may have heard what entropy is. If some of you guys are engineers, then probably in the first year of engineering, we have a subject called as thermodynamics, and there is a law of thermodynamics. I think it is the 0th law, which talks about that the entropy of a system always increases. Now, I am not a mechanical engineer, so I don't know too much, but I know one thing for sure, that entropy talks about a concept of chaos. Okay, and we look at the chaos in a system, and entropy is a measure of the chaos in a system. Okay, so what do I mean by chaos? By chaos in our terms, I mean things that are not homogeneous. Homogeneous is again another big word. Okay, so homogeneous basically means if I have a pure subset or not. Okay, if I have a pure subset, that is all my data is of one type, I would say that it is homogeneous. Okay, so in our sense, if I look at my target variable, if I look at my last node, false. Okay, and at this point, if all the values that I have are yes, then I will say I have a homogeneous system. If I have 5 values, of which 3 are yes and 2 are no, I would say that the homogeneity, I have less homogeneous. Okay, homogeneity. Okay, I am not able to pronounce this well. Homogeneity of the system is less. Okay, so entropy basically is a term that helps us understand if we have a pure subset or not. Okay. Let us look at the formula for entropy. The formula for entropy is basically minus p log to the base 2p minus q log to the base 2 of q. Okay. On the x-axis here, actually, if you see, we have again hidden by this advertisement. You can see that on the x-axis I have 0 here, 1 here, and we have something called as p that we are plotting. Okay. When p is closer to 0, we can see entropy by this graph. Closer to 0, entropy, this blue line, is equal to 0. When p is closer to 1, we can see at this point here also entropy is equal to 0. And when p is equal to 0.5, then we see the entropy is maximum. Okay. So what this is trying to tell us is p is basically the probability or the measure of how many items do I have. Okay. If all the items I have is yes, then my p is equal to 1. If all the items I have is no, my p is equal to 0. If I have some number in between, then p represents that value. Okay. Entropy tells us that if all values are same, okay, all values are homogeneous, my entropy is 0. Okay, my entropy is 0 or minimal. As I start mixing things, my entropy will grow higher, and I will have a higher entropy. Okay. So let us look at an example so that we can see what this means. So here we are trying to say to build decision tree. Okay, I forgot one term here. For decision tree, we'll be using an algorithm called as ID3. Okay, again, I have forgotten what ID3 algorithm. What is the full form for ID3 algorithm? Nonetheless, this is the algorithm that we would want to implement for creating the decision tree. And this algorithm, it requires us to understand the term entropy. Okay, so we are seeing the term entropy. Now, to build a decision tree, there are two types of entropies that we have to calculate. One is entropy of the target, and second is the entropy of the target with an attribute, with a feature. Okay, here we will look the entropy of a target. This is the formula for entropy. So this is the same formula as here. Here just we had two classes, P and Q. But in a more standard way, if I have C number of classes, my entropy will go from minus P1 log to the base P1 log to the base 2 P1 minus P2 log to the base 2 P2 minus P3 log to the base 2 P3 and so on. Okay, so I represents the number of classes we have. For this data, that is whether we play golf or not, we have only two classes, yes or no. So we say C is only 2. So I go from, my equation becomes equal to minus P1 log to the base 2 P1 minus P2 log to the base 2 P2. Okay. If you look at your data of playing golf, we have 14 data points. We have 14 data points, of which we have 9 yes, and we have 5 no. Okay, we have 9 yes values and 5 no values. So we are trying to evaluate what is the entropy of the target variable. Okay, so we say play golf has 2 values, yes and no, 9 yes and 5 no. So we'll say the entropy of playing golf is equal to the entropy of 9, 5. Okay, 9, 5 is equivalent to having the entropy of 0.64, 0.36. So how do I come from 9.5 to 0.64, 0.36? Simple. I take 9 and divide it by the total number of terms, which is 14. So 9 by 14 is 0.64 and 5 by 14 is 0.36. Okay. So I say entropy of 9, 5 is entropy of 0.64, 0.36, which according to our formula here is minus p, minus probability of being a yes, minus p, log to the base 2 of p, minus q, or if this is p1, this is p2, minus p2, which is 0.36, log to the base 2 of 0.36. Okay. So here, if I evaluate this, it comes out to be this number, which is 0.94. And 0.94 is a rather large number. Okay. So if we are plotting our entropy term, 0.94 is somewhere around here. Okay. This is 1. So we are somewhere on the upper end. Why are we somewhere on the upper end? Because we have a mixed box. Okay. Not all of them are yes, not all of them are no. We have 9 values of yes, 5 values of no. So we have a good representation of no. So we have disorder in the system, or our bucket or our subset is not pure. That is why we have a high entropy number. Okay. So I hope you have understood what is entropy of a target and how we can evaluate it. Let us go ahead and let us look at the second type of entropy. That is the entropy of the target with the attribute. Okay. Attribute is nothing but feature. Okay. So we look at playing golf again. And now when we look at playing golf, we look at one of the features. One of the features we look at is outlook. Okay. So we saw there were four features, outlook, humidity, temperature, and windy. We'd say, let us click an example of outlook. Outlook feature has 3 different options. We have sunny, we have overcast, we have rainy. Okay. Playing golf, if I divide as yes and no, will be divided into 9 and 5. The 9 examples of playing golf, so 3 plus 4 is 7, plus 2 is 9, and 2 plus 3 is 5. So we have 9 examples of yes, playing golf, 5 examples of no, not playing golf. Okay. Out of the 9 examples, 3 of them are sunny, 4 of them are overcast, and 2 of them are rainy. Okay. So what I'm doing is, I'm going here, I'm looking at this data, and I'm looking at these examples of yes. Okay. So these are the examples of yes, playing golf. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, these are the examples of playing golf. In these 9 examples of playing golf, we are finding out how many are overcast. Okay, how many are sunny? So we have 1, 2, 3 as sunny. Okay, 3 sunny. How many overcast? I have 1, 2, 3, 4 as overcast. And how many rainy? So I have 1, 2 rainy. Okay, so we are just trying to break down out of the 9 yes that we have for this one feature outlook, what is the breakup? Okay, so and after making the breakup, we're just noting it down here. Out of the 9 playing golf, we have 3 sunny, 4 overcast, 2 rainy. Similarly, we can continue the exercise where we'll say, okay, for not playing golf, how many sunny do we have? We have 2 sunny. How many rainy do we have? We have 3 rainy. Okay. And on a total, okay, here we have the total. Whether yes or no, out of the 14 examples that we have, 5 of these examples are for sunny, 4 of these examples are for overcast, and 5 of these examples are for rainy. That gives us total 14 datasets. I hope you understand how we can create these or count these individual numbers. Okay. So even before going ahead, if I have to ask you the question, okay, what is the homogeneity or what is the entropy of sunny, overcast, and rainy? Which one has the minimum entropy? Okay, out of sunny, overcast, and rainy, which feature has the minimum entropy? What will be your answer? Mm-hmm. One person is saying sunny. Okay. Okay, my question is, which of these three, sunny, overcast, and rainy, will have the minimum entropy? Okay. Okay. So I've got mixed answers. That tells me that you have not understood well. Many of you are writing it rightly. So yes, the answer is overcast. Overcast has the minimum entropy. Look at here. If you remember our entropy curve, okay, our entropy curve is something like this. On the x-axis, we have probability, or we have distribution of division. On the y-axis, we have entropy. Okay. So here, entropy says that if I have all as one, all as no's, or all as yes, then my entropy will be 0. If I have a mixed number, my entropy will be high. So if I look at sunny, I have 3 yes and 2 no's. So I would say that I have a mixed value. I will have a high entropy. Okay. If I look at 4 and 0, I said, oh, great. Out of the 4 examples, all examples belong to one category. Okay. All examples say yes. Entropy will be 0. If I look at this, again, a mixed bag, I will have a high entropy. So overcast is the right answer. The attribute that will have the least entropy is overcast. Nonetheless, let me go ahead and tell you the second formula. The second formula is, how do we evaluate entropy of a target with an attribute? For that, we will use this formula. The entropy of the target with an attribute is given by the summation of all classes. Okay, so for all the different categories, we will sum it up. What is the summation? Probability of that category, okay, probability of that data with the entropy for that data. Okay, probability of the data with the entropy for that data. Let's look at an example. So the entropy of the target playing golf for the feature outlook, for the attribute outlook, is given by this term. So we see the feature outlook has 3 options: sunny, overcast, rainy. So this probability, or the entropy of playing golf with outlook, is probability of sunny multiplied with entropy of sunny plus probability of overcast times entropy of overcast plus probability of rainy times entropy of rainy. Okay, so here when I say entropy of sunny, I'm basically saying entropy of the target with respect to sunny. Okay, this 3-2 is yes and no. Okay, these are examples of yes and no. Entropy of the target, but only for the sunny feature. Entropy of the target only for overcast feature, and entropy of the target only for rainy feature. So this will be the formula that we are trying to evaluate. Now we can easily say, what is the probability of sunny? So out of 14 examples, 5 are sunny. So probability of sunny is 5 by 14. Probability of overcast. So out of 14 examples, 4 are overcast. So probability of overcast 4 by 14. Probability of rainy, out of 14, 5 are rainy. So 5 by 14. Let's look inside. What is the probability of 3, 2? What is entropy of 3, 2? So for entropy, we'll go back to our previous formula and we'll implement something like this. This will be minus 3 by 5 log to the base 2 3 by 5 minus 2 by 5 log to the base 2 2 by 5. Okay, I'm just using our formula from before. Okay, if you remember here, let me just show you. Our formula is this. That is, the entropy of 9, 5 is evaluate the individual probabilities, then minus of that number log to the base 2 this number, minus of the second number log to the base 2 the second number. So if I just do this for 3 comma 2, it comes to expansion of this formula. If you evaluate this, you end up with the number 0.971. Okay. So you say, okay, entropy of 3 comma 2 is 0.971. Entropy of 4 comma 0, it is 0. Okay. How? We say, okay, entropy of 4 comma 0, it comes out to be, so 1 times log to the base 2 of 1 minus 0 times log to the base 2 of 0. Okay. Now, log 1, if you have your math right, is equal to 0. And 0 times something is equal to 0. 0 minus 0, you end up with 0. So we say entropy of this term comes out to be 0. Interestingly, entropy of this term, that is 2 comma 3, also comes out to be 0.971. So we see entropy of 3 comma 2 is equal to entropy of 2 comma 3, which we understand because the internal terms are just summation. This term and this term, if you change the order here and order here, so the value will still remain same. Okay, so both these terms have a pretty high entropy value, but 4 comma 0 has a very low entropy value. So when you evaluate this entire thing, we come up with the number 0.693. Okay, so we have just learned how to find the entropy of a target with an attribute. Okay, let me go ahead. And there is one last term that we need to understand. Okay, that is, what is the information gain? Okay, and information gain is based on the decrease in entropy after a data set is split on an attribute. So once you take an attribute and you split on that attribute, what is the gain in information? Okay, and this gain in information is simply evaluated by the entropy of the target minus the entropy of the target with the attribute. If we do the subtraction, we will find out what is the gain of the target with that particular attribute. Okay. Yes. So finally, we are now ready to talk about the procedure, or talk about the algorithm that helps us evaluate decision tree. We have looked at the nuts and bolts that make this algorithm. Let's look at the algorithm now. So in this algorithm, we say the procedure for doing decision tree is such. First, step 1, calculate the entropy of the target. Okay, easy job. We have seen how to do that. Just evaluate the number of terms. What are the number of yeses? What are the number of no's? And evaluate entropy. So this is a simple job. Calculate entropy of the target. Second, the data set is split on different attributes. We will try to split the data set at this point on each of the features. There were 4 features: outlook, humidity, temperature, and windy. Okay, we will try to split the target based on all these 4 features. Okay. How do we split them? First, we will find the entropy of each branch. For each of the features, we will evaluate the entropy. Then it is added proportionally to get the total entropy for the split. Okay. For each feature, we will find the entropy of each branch. We will add it together to get the entropy of the entire split. We will get the resulting entropy and subtract it from the original entropy. And we will find something called as the information gain or decrease in entropy. Okay. So the steps that we did here, okay, that is, first find the entropy of the target. For each of the features, so this is one feature, for each of the 4 features, evaluate this entropy. Evaluate the gain for each of the 4 features. And that is what we have here. Okay, evaluate gain for each of the 4 features. Once we go to the example, this will become clearer. But for now, just remember the terms. Okay. Once we find the information for each of the splits, we will choose the attribute with the largest information gain as the decision node. So at this point, whichever feature has the largest information gain, we will say that feature is our decision node. Okay. Now, once we have found a decision node, we will take our values and go ahead. Now, how do we stop? if after splitting, if a particular entropy is 0, that's it. Then we say that is a leaf node. Okay, entropy being 0 means we have a pure subset. If we have a pure subset, we have no more reason to further split. If there is no reason to further split, we will say we will stop the node there. That is, we have a leaf node. If the entropy is not equal to 0, we will further need to split. How do we split? Using the same idea as we did in step 2. Okay, using the same idea as we did in step 2, we will further split the data. And we will continue to do this. We'll keep doing this recursively till we have all branches as leaf nodes. Okay. Once we have all branches as leaf nodes, then we will stop our recursive implementation. I know this is very confusing. Let's look at the steps in terms of the data that we have seen. Step 1, calculate the entropy of the target. So we have already done that. We see it comes out to be 0.94. Okay. So step 1 is done. We have calculated the entropy of the target. Let's go ahead. Step 2. The data set, okay, for each of the features. So there are 4 features: outlook, temperature, humidity, and windy. For each of the 4 features, evaluate the information gain. Okay, sorry. These 2 values are hidden, but I know that these values are smaller. Okay. Nonetheless, let us look at how do I evaluate information gain. So we have seen for outlook, how do we evaluate the entropy of the target with an attribute, which is this part. So we take the entropy of the our initial entropy, which is 0.94. From that, we subtract the entropy of the target. So for I think for outlook, we had come with some 0.67. You can go back. 0.693. And when you subtract this, you end up with something like this, 0.247. And we say that that is the information gain for outlook. So we do it for all 4. We do it for outlook, we do it for temperature, we do it for humidity, we do it for windy. Whichever has the largest information gain. So this one has 0.029. So this is definitely not larger than this one. These 2 are hidden, but I know that both of these guys are less than 0.247. Okay, so just trust me on this one. Once we see what is the highest information gain, we will choose that as our feature. Going ahead, we'll say choose the attribute with the largest information gain as our node. So we say outlook, therefore outlook will be the first node. Why? Because it has the highest information gain. Then once we have outlook, we say outlook has 3 options: sunny, overcast, or rainy. Let me show you an example of overcast. Okay, so I take all the data that is pending. Okay, that means I go back here to my original data. Let me take you quickly. From this data, we will only choose those features which have overcast. So 1, 2, 3, and 4. Okay, these 4 columns now. These 4 rows will now be the candidate that is left at this point. Okay. For these 4 rows, since we have already chosen overcast, since we have already looked at outlook, we will say outlook is not a deciding feature anymore. Then we are left with 3 features: temperature, humidity, and windy. Okay. We'll look at temperature, humidity, and windy as features and play golf as target. Okay. So let me go back. Once you do that, you look at temperature, humidity, and windy as your features and play golf as target. This becomes your data. For this data, we now evaluate what is the entropy. So we say entropy here, since we have all 4s as yes, the entropy is 0. Okay. Since the entropy is 0, we can say that this is a leaf node because this branch has entropy 0. This is a leaf node. We don't need to further split. So we give the value as the value here, which is yes, and we stop splitting overcast. If you look at the example of sunny, then we say, if I shortlist based on sunny, these are the 5 values that I have. Of the 5 values that we have 3 values of yes, play golf, 2 values of no, don't play golf, which gives us an entropy of 0.971. Once we have that entropy, we need to now choose which is the next feature we will go for. Okay, what should be the next feature? Do we go for temperature? Do we go for humidity? Do we go for windy? So let us just quickly view the data. Which of these features will give me the least entropy after this point? Can you look at these features and tell me which one will work out? Do we choose temperature? Do we choose humidity? Or do we choose windy? Which one will have the least entropy? Okay, we have one example of humidity, temperature, temperature. Okay. Okay. So, no. let me explain. Let me explain how will you evaluate this. Okay. So now we will say that my target is play golf. I have 3 features: temperature, humidity, and windy. We will look at the examples of these guys and see how they are dividing the target variable. The temperature has 2 options, mild and cool. Humidity has 2 options, high and normal. Windy has 2 options, false and true. Okay. So if I look at temperature, for mild, so if let me say for temperature and play golf, yes and no. Let me do it a bit neatly. Okay, let me go here. So I say play golf can have the values yes or no. Temperature can have mild or cold. So how many yes do I have with mild? So mild, I have 1 yes, mild 1 yes, mild 1 no. So I have 2 yeses and 1 no for mild. What about cool? Well, I look at cool, I have 1 yes and 1 no. So I'll say 1 yes and 1 no. Okay. Then, if I try to evaluate the entropy here, I will say that yes and no are mixed. Okay. I have a mixed set both for mild and both for cool. Since I have a mixed set, I am guessing I will have a high number of entropy. Okay. Of course, you can evaluate this, you will end up with a high number of entropy. Let's look at another example. If you look at, if you look at humidity, I will say playing golf, yes, no. Humidity as high and normal. So I have, with high, I have 1 yes, 1 no. With normal, I have 2 yes, 1 no. Again, high entropy. It's a mixed set. Let's look at windy. So playing golf, yes and no. Windy can be false or true. If windy is false, I have 3 examples of yes, 0 examples of no. If windy is true, I have 0 examples of yes, 2 examples of no. Okay. Now if I look here, I see that my data is neatly divided. I have either all as yes or I have all as no, depending upon windy is false or true. This will give me the least entropy, right? Because I will have a pure subset. Because I have a pure subset, I will have the least entropy. So our next choice should be, I should choose windy, because if windy is false, all cases point towards yes. And if windy is true, all cases point towards no. I hope that makes sense. Thus, once we choose outlook and outlook is sunny, we will choose windy as the next feature. We will not use temperature. We will not use humidity, because after I reach temperature, I will have a mix set. If temperature says mild, I don't know. Do I say yes or no? Because I have two examples of yes, one example of no. If temperature says cool, I don't know what to choose because I have one of yes, one of no. So temperature is a bad feature to choose. If I look at humidity, I have, when humidity is high, I have again a mix set, yes and no. If humidity is no, I have again a mix set, 2 and 1, yes and no. So humidity is a bad example. But windy is an excellent example. Why? Because if windy says false, I know I have always to say yes. And if windy says true, I know I have to always say no. That says that I don't have to go deeper into my tree. My entropy, my information gain will be highest if I choose after sunny, I choose windy. And that is the reason that we choose windy here. Okay. Of course, we will use the information gain formula, entropy formula to evaluate this. But even logic tells us what needs to be done next. So with that strategy, we can go ahead and we can complete the tree. I hope now we understand why outlook was chosen as the first feature. After sunny, why we are choosing windy. After rainy, why we are choosing humidity. And why does overcast stop here? Okay. So once we have this decision tree, we can write it down in rules. Rule 1, rule 2, rule 3, rule 4, rule 5. How many rules will we have? As many leaf nodes. Okay. As many number of leaf nodes we have, that many rules we will have. Rule 1 is for this path. It says if outlook is sunny and windy is false, then say yes. If outlook is sunny and windy is false, say yes. We'll play golf. Second rule, if outlook is sunny and windy is true, say no. So that is our second rule. Like this, for each of the branches, you can come and you can make the different rules that we have. And these rules will help us to use, these rules are basically decision tree trying to interpret what goes into that target function. Okay, and decision tree says that we can create a tree like this, and the tree will help us navigate which data we go for and how do we go for it. Okay, I hope this concept is clear. Let me then quickly move to the next part, which is a random forest. And random forest is basically an extension of the decision tree. And okay, the idea here is this. Okay, okay. Let me directly get inside and then explain. Okay. So a random forest basically is made up of multiple trees. Okay, and the idea is there is wisdom in the decision of crowds. That means if I actually want to make a prediction, I should consider multiple people and then decide what to do. So let's say for most important decisions of our life, whom to marry, which job to take up, what education to pursue, what career to pursue, we generally don't take decisions based on what we understand, or we should not take decisions based on only our inputs. We should ask people around. You would discuss with your parents, you would discuss with your counselors, with your teachers, with the mentors, with your friends. And once we've discussed enough, we can take all of their inputs, and those inputs can help us to guide or to decide better what we need to do with our life. Okay? And once we have those decisions, then we can take probably the best out of them or combine what most people say and then use that for our prediction or use that for our decision factor. Okay. Similarly, even for data sciences, if we just depend upon one algorithm, that is one option, but we could also depend upon multiple algorithms and decide what those multiple algorithms are predicting, and based on that we use our prediction. Okay, so see, these kind of methods where we depend upon multiple algorithms are called as ensemble methods. They are called as ensemble methods. Now, for ensemble methods and random forest, we say that random forest is basically made up of multiple trees. So we have, let's say, an algorithm called as random forest, and it makes use of decision tree 1, decision tree 2, decision tree 3, decision tree 4, and decision tree 5. Okay, let's say for argument that we have 5 decision trees, and what these 5 decision trees say about playing golf, yes or no, that the majority of that will decide what random forest will do. Now the question is, if all decision trees are same, okay, if they are created in the same way, if they operate in the same way, then I have one decision tree or I have 10,000 decision tree, my answer will not change. So we know for a fact that when we talk about the decision trees that make up random forest, we want these decision trees to be different from each other. Okay, we don't want the decision trees all should be same. If they are all same, this is not wisdom of crowds. Okay, wisdom of crowds means that we are taking into consideration all different aspects. Okay, so just like I said, for an important decision, we will ask different kinds of people. You see, these different kinds of people are all having different experiences of life. If you just ask your friends and maybe 5 friends, most of your 5 friends would be similar. Okay, they would not have, they would be of your age group, they have the same similar experience. But if you mix it up, if you ask your parents, if you ask your mentors, if you ask your teachers, if you ask your friends, you're talking to different kinds of people. And these different kinds of people come with different experiences of life. And thus they will help you take a better decision, a more informed decision. So wisdom of the crowds demands that these different decision trees are actually different from each other. They are not the same. But the question comes, if I have the same data, and from the same data I'm trying to create a decision tree, will I not end up with always the same decision tree? Yes, from the same data and same option, same configuration, we will always end up with the same decision tree. That is where the term random comes into place. We have to bring some kind of randomness to create our decision trees. Now this randomness can come in 2 ways. One is called as bagging, the other is called as feature randomness. Okay, so let me quickly show you what bagging is and what feature randomness is. See, we had 15 data points. So let's say I have maybe 5 data points, 1, 2, 3, 4, 5. These are my data points, and using these data points, I will create decision tree. So let's say I create decision tree 1 using these 5 data points. Now to create decision tree 2, what does bagging say? Bagging says is, let me take one element from here. So I'll take one element from here. I will say, using the data 1, let me take another element from here. So now when we take another element, I have the option to choose anything I want. I will randomly choose one number. So let's say I take the number 3. I will randomly choose one number. I may choose 1 again. I may randomly choose 2 or randomly choose 4. So what we now see is, when I try to randomly pick items, I am allowed to pick the same item multiple times also. So I end up with 1, 3, 1, 2, 4, which basically says that out of the 5 examples, I have not used data 5, and I have used 1 2 times. Okay, which means that this is a different input going to the decision tree. And since this is a different input going to the decision tree 2 will be different from decision tree 1. Okay. Not very different, but different. Similarly, I take another set of examples for decision tree 3, and maybe I'm using only 2, 2, 1, 3, 5. Okay, so I have missed out 4. So when I do something like this, I'm getting a different decision tree. So these different decision trees can be generated using bagging by this method, where we are providing different data to our models. Since we are providing different data to our models, we will end up with different decision trees. We can use the majority vote of these decision trees to predict for random forest. Okay. The other method that we can use for randomness is called as feature randomness. Okay. What does feature randomness say? That let's say we are making decision tree 1. I have 4 features to play with. I have outlook, humidity, temperature, and windy. Okay. So let's say in the first phase, I say to this decision tree that I do not allow the usage of humidity. That for the first decision, I cannot consider humidity as a factor. I can only choose between outlook, temperature, and windy. So based on entropy, you will choose one. After choosing one, let's say you choose outlook. After choosing one, to further divide, I will say randomly, I would say you are not allowed to use windy. So if I don't allow to use windy, here you have left with only humidity and temperature. So based on these two, you will make some decision. Okay. So we saw what feature randomness is doing. Feature randomness, it purposely disallows certain features to be included in the decision of making the next node. Okay, and that will add again another level of randomness to our data. Okay, we will end up with different decision trees because of this. So there are multiple ways of doing this. 2 very commonly used ways for random forest is bagging and feature randomness, where we decide how we will be making different trees. Once we have these different trees, the answer is very simple. We will take a vote. Let's say decision tree 1 says yes, play golf. DT says yes, play golf. DT3 decision tree says no, don't play golf. No and no. Then we will say 3 no's, 2 yeses. We will go for no. Okay. So that is how we will use an algorithm called as random forest. Okay. It's a very simple algorithm. It is based on decision trees. It's an ensemble method. Okay. So we'll stop here today. In the next class, we will continue ahead with our validation methods and so on. Okay. Let me stop sharing. Okay, Nirja ma'am, I will disconnect for now. Okay, I have a question. Let me answer the question. It is, if there are equal dt, then what will we choose? Okay, so if there are equal dt, it doesn't matter. You can choose either yes or no. Any of them will work out fine. Okay, since our algorithm itself is confused. A better way is, if I have even number, let's say if I have yes or no, then I can choose odd numbers of decision trees. That way I will never end up with a tie. Okay. But there are different ways of handling. Either one of them works out fine. Okay. Thank you so much. I'll leave for today. We'll meet tomorrow. Have a good day. Bye-bye.